Okay, so now that we've looked at one sample inference for quantitative data for means, let's go ahead and look at the chance here that we possibly make a mistake in our decisions based on our inference procedures. So, sorry, hiccup. Okay. So, in general, if the null hypothesis is true, we should fail to reject the null. We never say that we accept it, but we say that we fail to reject it, meaning we don't have enough evidence to claim otherwise. Likewise, if the null hypothesis is false, then we should reject it. We are wanting to reject a false claim. We call this the power of the test. There is power in rejecting a lie. Now, if we made a mistake, let's suppose we actually got our wires crossed. And so you can see that these two decisions are the correct decisions, but what if we went the other way? So let's say that we rejected the null hypothesis, given the null was actually true. This results in what we call a type 1 error. Now, if we fail to reject the null hypothesis, given the null was actually false, then we commit a type 2 error. So we have this diagram here that helps us to organize these pieces of information. Now, considering these decisions, you can see that it's going to depend on the context of the question. So you might hear that a type 2 error is always the worst type of mistake. That's false. We actually don't know. It depends on the context. And like statistics, it's always going to be that way. Now, I will say the helpful way to remember it is that when you fail to reject, that's usually a type 2 error. So there's a little help there. Now, we do have some probabilities assigned to each of these types of errors. For example, the type 1 error, which is rejecting the null, given that the null is true, is alpha. And you notice this looks very similar because it is, in fact, our significance level for the hypothesis test that we are conducting. And so that's our rejection region. That is the same thing. We build our sampling distribution based on the null hypothesis claim. Thus, rejecting it, given that it's true, would lead us to an alpha level, usually 0.05 unless otherwise stated. Now, type 2 and power are a little trickier. They're not going to ask you to compute it by hand, unless you're the question 6 in 2018. But other than that, typically they'll provide one of these values to you. And what's more important here is to know how changing certain scenarios within the circumstances of the problem affects each of these types of probabilities. And actually, in the last video in Unit 5 that I made about powers and error, I was a little too happy with changing the significance level for the other quantities here, so I'll make sure to address that in this video. And in case you are ever forgetting what's happening here, a type 1 error is what we call a false positive, a rejection given that it's true, and then type 2 is a false negative, failing to reject something when it's actually false. And so we can see here that in this case, a type 2 error would be much more significant because perhaps this mom-to-be now starts practicing a lifestyle that might not be the most beneficial for the baby. And alas, again, type 1 and type 2 errors depend on, or the severity of them depends on the context of the question. So let's take a look here, and I actually did borrow the 2018 question. But systolic blood pressure is the amount of pressure that blood exerts on blood vessels while the heart is beating. The mean systolic blood pressure for people in the U.S. is reported to be 122 millimeters of mercury with a standard deviation of 15. The wellness department of a large corporation is investigating whether the mean systolic blood pressure of its employees is greater than the reported national mean. A random sample of 100 employees will be selected, and the systolic blood pressure of each employee in the sample will be measured, and the sample mean will be calculated. If the person's systolic blood pressure is 122 or less, no action is taken. If a person's systolic blood pressure is greater than 122, then treatment using medication and or diet and exercise is to be started immediately. So let mu represent the systolic blood pressure of all employees at the corporation. Let's create a set of hypotheses and then identify some errors here. And so I added the last bit there because we needed some consequences for our errors, but in the original question, that was not there. So we are going to create our null hypothesis, which is the claim, and then our alternative hypothesis, which is what we're testing for. Now, we've already been given the parameter of mu, which is the true mean systolic blood pressure, and our legal limit, as I call it, is going to be 122, meaning that at 122, we're fine. So if it's less than, that's great. So technically this inequality should be less than or equal to, but for the purposes of this course, we'll just call this our legal limit, meaning we're not going to get in trouble if it's at 122. Now, the dilemma happens when you are greater than 122. And we're just going to go ahead and identify some consequences here. So, if your systolic blood pressure is 122 or less, we were told that there was no action. Now, if it's greater, then we're going to have some treatment involved, which could include meds, diet, and exercise. I'm just going to leave that as that. So, using now this given information, go ahead and identify a type 1 with the consequence, type 2 with the consequence, and the power of the test with its consequence. And yes, consequences can be positive. So I'll leave this here for you. Go ahead and pause the video and attempt these out, and then we'll go over the answers in just a few moments. Okay, so let's go ahead and review this. But in a type 1 error, we reject the null when it's true. So here we claim the systolic blood pressure of the employee is greater than 122, when in fact it actually is 122 or less. So we can cause an employee to start treatment when they did not need to change their lifestyle. So maybe this results in a few extra expenses that they weren't planning on. Now here, a type 2 error would be that we claim the systolic blood pressure for the employee is 122 or less, when in fact it's actually greater than 122. Thus, we issue no treatment when treatment should have been issued, which could result in further health issues and complications down the line. So we didn't catch the problem early enough. Now, the power of the test is rejecting a false null hypothesis. So here, we claim that the systolic blood pressure is greater than 122 when in fact it actually is. Thus, we begin treatment for someone who is actually in need of treatment. There's power there. We might be saving their life. Now, again, here we're seeing this pattern that the type 2 errors seem to be more severe, but again, just depends on the context. And here, it would be more severe because if we're not issuing treatment when someone needs it, this could cause further complications. Whereas in a type 1 situation, we're giving someone the treatment when they don't actually need it, so this just might improve their quality of life. Maybe not the financial element, but alas, that is beyond the scope of this course. Now, the power of the test has a few unique components, and so I'm going to go ahead and fill this in here. But essentially, the power of the test is the probability of correctly rejecting a false null hypothesis. A type 1 error and the power are directly proportional, whereas a type 2 error and the power are inversely proportional. And there's a few things here that we can do that will change the power of the test as well as the type 2 errors. So I'm going to go to this applet here to do some simulations. Again, we did this back in Unit 5. But suppose our hypothesized null is here at 0, centered at 0, and the true population mean is actually here at 1.5. I'm just doing a greater than, so a one-tailed test on the right-hand side here. And you can see the different probabilities. So a type 1 error, a typical significance level of 5%. And we can see our type 2 error is the blue here, and the power is the green. So you can see the red and the green are shaded on the same side, and the blue is on the opposite side of that. Now, we really only know the relationship between power in type 1 and power in type 2. And for some of these situations, we could change to type 1. So let's go ahead and take a look here. But the first one says, let's increase the sample size. So I want to make sure you can see those probabilities. Right now I have a sample size of 30. So let's see what happens when I go to a sample size of 80. Well, we saw that my type 1 error did not change, but my type 2 error decreased and my power increased. So our first blank here is going to be that when we increase the sample size, the power of the test increases and the type 2 decreases. And we can see the opposite case as well. Let's say I took a small sample size here at about 10. Well, now the power decreases and the type 2 error increases. So I'm going to go back to my sample size of 30 so that we can use our central limit theorem here. Now, if I change my significance level, let's say I increase to 8%, a little over 8. But we can see, of course, I'm changing alpha, so alpha should change. But also we see type 2 has gone down and the power of the test has also increased. So again, I'm going to go from my original here at 5%. And why is this happening? Well, you can see as I'm increasing this rejection region, more of the tail is being exposed to the power in that rejection region. So we're increasing that area, which means we should be increasing those values. So here, the power of the test will increase, alpha will increase, and we can see that type 2 will decrease. Now, I'm going to go back to my original here at 0.05. Okay, let's suppose that I'm going to change the distance now between our, I'm going to put my face over here in the middle. There you go. Let's suppose I change the distance between our claim and our truth. So let's see what happens when I get closer. When I get closer to it, we can see that type 1 doesn't change, but type 2 increases and power decreases. Now, let's say I actually increase the true value. So you can see as I'm increasing the value, so I'm going to do this again, as I increase the distance from the truth and the claimed null hypothesis, power is going to increase and type 2 will decrease. And again, our significance level hasn't changed at 5%, so that one stays neutral. And actually, whoops, it's going to be the same thing, but I should have put that in the fourth row here. And the last one is just the standard error. Now I'm going to go back to here at 1.5, and I'm going to adjust something on my screen that I don't think you'll be able to see. So let's suppose I actually change my standard deviation. So I'm going to increase my standard deviation. And when I increase my standard deviation, we're about 50-50. So actually here was our original standard deviation at 3. Okay, so I'm going to increase it now. So if I increase the standard deviation, so one more time. Sorry, y'all, I also missed that. So here I am at 1486. When I increase the standard deviation, now I'm at 3486. So as I increase the variability, I'm decreasing the power, which means if I decrease the variability, I would increase the power. So as we can see here, typically power and type 1 are directly proportional, specific to the significance level. And then these other elements, we can see this inversely proportional relationship between type 2 errors and power of a test. So that's just a fun way to look at that simulation there. So let's take a look at some multiple choice practice questions. Typically, errors and power show up as multiple choice questions, but you may have a section in the FRQ that asks you to justify which type of error you made, how you can change one of the errors, etc. So it's always good to know the concepts behind. But here we have a one-sided hypothesis test. It is performed with a significance level of 0.05. Suppose that the null is false, and we use a level of 0.01 instead of a significance level of 0.05. Well, we're decreasing the significance level, and that would result in a decrease in the power. And if I decrease the power, the probability of a type 2 error should increase. So the probability of type 2 will increase, and the power of the test will decrease. Now here, another situation, and mostly logic. A medical doctor uses a diagnosis to determine a test whether a patient has arthritis. A treatment will be prescribed if they think they have arthritis. We're going to use the following Nolan alternative. And so if the patient does not have arthritis, well, what happens? There would be no treatment. And if the person does have arthritis, there will be a treatment. So here, which of the following would result in a type 2 error? So in a type 2 error, we fail to reject. So we believe the patient does not have arthritis when in fact they actually do have arthritis. So here, we are failing to diagnose arthritis in a patient who actually has arthritis. And you can see that each of these situations results in a type 1, type 2 power or correct decision here. So failing to diagnose in someone who has it. So we fail to reject, but it's actually false. And then the last question here, I'm running out of time on my free trial. So go ahead and read over this, pause the video, and then let's go over the answer. Okay, so hopefully you were able to obtain this answer. There is power in rejecting a false claim. So here, we believe the driver is speeding when in fact they actually are speeding, thus we issue a ticket and the correct consequence. So that's just some examples there of powers and errors that you might see in the multiple choice section, as well as potentially some FRQ questions. So good luck.